Hello everyone. In this video, we are going to discuss about the most important concept, Word2VEC. So now look at this. So what do you understand from this? So you can see that here there is red and here I have red, yellow and green. The corresponding red column is 1 and the remaining 2 are basically zeros. So again, there is red, 1, 0, 0. Again, there is yellow. So I'm having 0, 1, 0, and then green. You can see that 0, 0, 1. So next for this yellow, it's going to be 0, 1, 0, right? So very simple. So something it is converting a text into numbers. That's what I could figure out from that. So let us try to understand what it is. Right? Fine. So Word2VEC is not a single algorithm, and it is an algorithm that takes corpora as an input and outputs it in the form of vectors. Right? So technically speaking, Word2VEC is a model to form or create word embedding. So it's a modern way of representing word, and each word is represented by a vector. Vector in the sense what array of numbers based upon embedding size. So the vectors are nothing but the weights of neurons. So if we set neurons of size 100, then we will be having 100 weights, and those weights are our word embeddings or simply dense vector. So this is not a single algorithm, but here we can talk about two techniques, the most important techniques, CBOW, skip gram model. CBOW means what? Continuous bag of words. And the next one is skip gram model. So both these are shallow neural networks which map words to the target variable, which is also a word. So both of these techniques learn weights which act as word vector representations. So basically it tries to find out a relation. It could be semantic relation or it could be syntactic relation between the words, which was not possible by our traditional TF IDF or frequency based approach. So when we train this model, each 1 hot encoded word gets a point in a dimensional space where it learns and groups the word with a similar meaning. So here the neural network is incorporated here is a shallow. So one thing to note here is that we need large textual data to pass into Word2VEC model to find out the relation within words or generate meaningful result. So what are we trying to do over here is Word2Vector is basically trying to find out the relationship, semantic relationship or syntactic relationship. So let us try to understand this, right? So still I can tell about this, right? You can see this over here, right? So here, what is the context word and target word, context word? So I like natural language processing. Now here, what is happening? The natural language processing. I like natural language processing. I like natural language processing. What this basically tells us, right? So what this basically tells us, that's what we are trying to identify. Just look at this and whatever is coming to your mind, you can just tell me. Right. So if you look into this, you could figure out. Can you figure out something from this? Yes. Right. So this is what the Word2VEC tells us. Next, let us try to understand CBOW, which means continuous bag of words. So the way continuous bag of words work is that it tries to predict the probability of a word in a given context, right? So this the way CBOW, that is continuous bag of words, work is that it tries to predict the probability of a word given a context, right? So a context may be a single word or could be a group of words. But for simplicity, I'll take a single context word and try to predict a single target word. So suppose we have a corpus C, which is equal to hey, this is sample corpus using only one context word, right? Fine. So the same thing I have written over here. You can see that the input is over here and the matrix here will be containing. So here it is showing us the no n one hot encoded code. So this is basically the output, right? So the matrix shown in the in this image is actually sent to three layers. So one could be the input layer, the second one could be hidden layer, third one is output layer. The output layer is a softmax layer which is used to sum the probabilities obtained in the output layer to 1. So now let us try to understand what has happened over here. So the corpus is converted into a training set for CBOW model. So the input is given below. The matrix on the right in the below image, I mean this image is basically giving me the one hot encoded, right? So below image in the sense like from data point 1, data point 2, what we can understand over here. Hey, this is sample, right? So this sample is corpus, right? So this is how we will be getting it. Yes. So what's happening here now? The target for single data point, say for example, here I have this one, right? So in case if I write for this one, what I'm getting 0, and for sample alone, this is what we are getting for each and every case, right? So the matrix shown in this above image can be sent into a shallow neural network with three layers, right? So input layer, hidden layer, and the output layer, right? And here the output layer is a softmax layer, and which is used to find out the probabilities obtained in the output layer, right? So now the here what we can try is the flow is as follows. So the input layer and the target, so both are one hot encoded of size 1 into V, where V is equal to 10, right? So here we are talking about this case basically. So there will be two sets of weights. One is between the input and the hidden layer. The second one could be between hidden and the output layer. So input hidden layer matrix size is V into N. Hidden output layer matrix size is N into V. So what is N here? Number of dimensions we choose to represent our word in, and it is arbitrary, right? So here what is the N over here? N is actually 4, right? So there is no activation function between the layers. So now the input is being multiplied by the input hidden weights and called as hidden activation. So basically it is just the corresponding row, the hidden matrix, input hidden matrix copied, right? So now what will happen? The hidden input gets multiplied by hidden output weight and the output is being calculated. Now the error between output and target is being calculated and propagated back. So we know about back propagation, right? So the weight between the hidden layer and the output layer is taken as the word vector representation of the word, right? So this is what happened here. So this is basically for a single context word. Now, if we have multiple context words, how does it work, right? So that is what the question that comes to our mind, right? So here you can see the three context words and it predicts the probability of a target word. So the input can be assumed as taking three one-hot encoded vectors in the input layer. Like it could be red, blue, or green. So the three input layer will have three 1 cross V vectors in the input and one cross V in the output layer. So the remaining everything will be same as for one context CBOW, right? So the steps will be the same. The calculation of hidden activation will change. So just instead of copying the corresponding rows of the input hidden weight matrix to the hidden layer, instead of that, an average is being taken and the corresponding, the average is taken over all the corresponding rows of the matrix, right? So the average vector is being calculated and it becomes the activation hidden activation. So say for example, if we have a 3 context words for a single target word, we will have 3 initial hidden activations. So which will be averaged element wise to obtain the final activation. So basically in both a single context word and multiple context word, we can see the images like how that basically changes, right? So here it is single, it is for multiple, right? So basically we will try to understand the difference between MLP and CBOW. So MLP, we know that it is the objective function is basically MSC, that is mean square error. But in CBOW, it is basically a negative log likelihood of a word that is given in a set of context, right? So log P WO by WI, right? So what is this basically means, like this is equal to exponential of this. So what is this WO means? WO is nothing but the output word divided by, and WI means the context words, right? So here we will be getting the gradient, right? So that is with respect to the hidden output weights and input hidden weights. So both will be different because MLP has sigmoid activations, but CBOW has linear activations, right? So MLP has sigmoid activations, but CBOW has linear activation. So the method, everything is almost the same. So the advantages of CBOW is it is probabilistic in nature, and it is supposed to perform superior to the deterministic methods, and its memory is low, and it does not, since its memory is low, it does not require huge RAM requirements and all, like a co-occurrence matrix, because it need to store 3 huge matrices, right? So what are the advantages of CBOW? It takes the average of the context of a word. And say, for example, ample, it can be a fruit or a company, but CBOW takes an average of both context and places, and places it in between a cluster for fruits and companies. So training a CBOW from scratch can take it forever if not properly optimized, right? So the next one is about the skip-gram model. So it also follows the same, almost similar to CBOW, but there is just a flip on the architecture. Here it is to predict the context given a word. So a word is given, it tries to predict the context. So say same corpus will be taken, and using that we build like what we are going to take the same corpus that we build CBOW. Hey, this is sample corpus using only one context word, right? So here you can see that the output context one, what are you getting? This, right? This, and then here, hey, right? This I have written, and then this is being hey, right? Again, this is sample corpus using only one context, right? So let us try to understand what this is. So here the input vector for skip-gram is going to be similar to one context CBOW model. And here the calculations are up to hidden layer activations are going to be the same. So what is the difference here? The difference will be the target variable. So we have defined a context window of 1 on both sides. So there will be only 2 1-hot encoded target variables and 2 corresponding outputs. It can be seen by the, it can be easily seen, right? So 2 separate errors are calculated with respect to the 2 target variables, and the 2 error vectors are obtained element wise to obtain a final vector, which is propagated back to update the weights, right? So the weights between the input and the hidden layers are taken as the word vector representation after training. So the loss function is going to be the same as CBOW model, right? So in case if you want to understand it better, you can look into this matrix style structure. So let us try to break down this image. You can see an input image of size 1 cross V, input hidden weight matrix of size V cross N, which is nothing but the number of neurons in the hidden layer N, and hidden output weight matrix size N cross V, right? So the output layer will be C of 1 cross V. So here we can say that C is the number of context words that I have taken 2, and V is going to be 10, and N is equal to 4, right? N is equal to 4. Hope it is clear. So now here the row in the red, right? So this is the hidden activation corresponding to the input 1 hot encoded vector. So it is basically the corresponding row of input hidden matrix copied. So the yellow matrix is the weight between the hidden layer and the output layer, right? The blue matrix is obtained by the matrix multiplication of hidden activation and the hidden output weight. So there will be two rows calculated for two target words. So each row of the blue matrix is converted into its softmax probabilities individually, like green box, right? So the gray matrix contains the 1 hot encoded vectors of the two context words, that is target, right? So the error is calculated by subtracting the first row of the gray matrix from the first row of the green matrix, right? And it could be done element wise. So this is repeated for the next row. So therefore, n target context words we will be having n error vectors. So element wise sum is taken over all the error vectors to obtain a final error model. So this error vector is propagated back to update the weights, right? So the skip-gram model can capture two semantics for a single word. Basically, it will try to have a two vector representations of apple. One is for the Apple company and the other one is for the product. And the next one is skip-gram with a negative subsampling outperforms every other method generally. So basically, like this CBOW and skip-gram are really very important to understand, because these concepts are really important. So the word embeddings or word vectors are basically the numerical representations of contextual similarities between words. So how it will work is like it will be finding the degree of similarity between two words and it will be finding the odd one out, right? It will be finding the odd one out and say that model doesn't match. And amazing things like is like we will be seeing this women plus king minus man, so that it will identify and tell us that it is a queen. And probability of a text under the model also it will give, right? So it can also be used for machine translation, right? So I hope this is clear to you. This is clear to you, right? We have seen Word2VEC, CBOW, and basically Ngram model. And I hope you really enjoyed this session. Thank you. Let's meet in the next session.